Hello, my name is Abed Kazantari. I'm a PhD student at Arizona State University, working at the Power Electronics and Control Engineering Lab, supervised by Dr. Ayam Malik. In this project, we have proposed a new modulation method for dual active bridge DAB as a part of EV chargers, and it's a DC-DC stage converter. And our new modulation method tries to minimize the conduction and switching losses of the converter, especially at the low voltage gain operation that's happening during the EV battery charging cycle. And let's first go through the slides to explain the circuit equations and the theoretical concept of the work. And next we will check the hardware and experimental results.
So let's go through the slides to explain what's the problem of the DAB operation, especially at the low voltage gain, and through the checking the circuit equations and the concept of our new modulation method, check how it can improve the efficiency of the converter in this mode. We are talking about the DC-DC isolated stage of the EV chargers, while the input voltage is fixed at 400 volt DC bus, and we know that the battery voltage is not fixed and it's changing, for example, from 250 volts to 400 volts during the charging cycle. So the DAB needs to operate at different voltage gains, starting from a low voltage gain up to a unit voltage gain. We know that DAB operates efficiently, and it has the maximum efficiency at the unit voltage gain. So the problem is that when we want to utilize the DAB at, for example, 400 to 250 volt corresponding to a low voltage gain. And we have proposed a new modulation method called the asymmetric half frequency modulation, or AHFM, to solve this problem. Our proposed method governs the DAB operation at the voltage gains close to unity, while the general voltage gain is the same, is around the half voltage gain, but it changes the duty ratio of the switches and the frequency of the modulation to make the circuit to work like unit voltage gain and improve the efficiency. I will present the theoretical analysis of the DAB and the assessment of the ZVS criteria using the generalized harmonic analysis method, and what's the impact of implementing AHFM at the primary bridge operation. And then we developed a conduction and switching loss optimization problem, which is aimed at selecting the optimal set of control variables, like the phase shifts between the primary and secondary, the phase shift at the primary bridge and the secondary bridge, called phi delta 1 and delta 2 depending on the modulation method, and we aim to select the optimal set of these control variables to minimize the switching network loss. And then we have applied this method, the AHFM, for the whole EV charging cycle, and to select the optimal modulation method at each operating point during the EV charging cycle, and we can probably switch between different modulation methods during the EV charging cycle to maintain the maximum possible efficiency. Here you can see the conventional DAB, and on the left you can see the waveforms for 400 to 250 volt operation, and you can see that for specific power, charging power, you can see the current profile here. You can see we have a peak profile with the maximum of 80 amperes, and we can utilize different gate control signal modulations with conventional modulation, including the single phase shift, dual phase shift, or triple phase shift. And we know that the triple phase shift provides a maximum flexibility in terms of the control variables that includes all three, phi, delta 1, and delta 3. And in conventional modulation, both the primary and secondary bridges work with a fixed switching frequency that we have considered 100 kilohertz as the switching frequency for this circuit. But now, what's the concept of our AHFM method that we have developed? Here, we want to have the same voltage gain as we have the V1, the input 400 volt, and we need to charge the battery at 250 volts. But the changes include changing the switching frequency of the primary side. We have the half frequency at the primary bridge. We have changed the duty ratio of the switches. Conventionally, we have the 50% duty ratio for all switches. Now we will have 75% duty for two of the switches like S1 and S4, and two other switches, S2 and 3, will work with the 25% duty ratio. And with these changes, we will have a square wave as the switching node voltage here. For example, if the input side is 400 volts, we will have a square wave between 0 and 400 volts here. And if we add a blocking cap here, after the blocking cap and before the external inductor, we will have a square wave without any offset that is varying between negative 200 to positive 200 volts, as you can see here. And as we need to work, and we have the secondary voltage of 200 or 250 volt, it's a low voltage operation, so the transformer is working at close to unity voltage gain, which makes the inductor and the transformer current minimum and less than the value in comparison with the 400 to 250 volt operation. And that's the main reason that it decreases the conduction loss and facilitates the ZVS condition and the soft switching, and consequently the reducing the switching losses. And as you can see here from simulation, for the same operation mode, we have a more flat profile for the current with the maximum of 55 amperes. To check the circuit equations, we have used the general harmonic analysis that uses the Fourier series for the equations to extract all circuit equations and analyze the circuit in the frequency domain. We have the voltages according to the primary and secondary voltage. We can calculate the inductor voltage, and accordingly we can calculate the instantaneous inductor current equation according to the equations depend on the control variables, including for the general case with the triple phase shift, we have the phi, we have the delta 1 and delta 2 appeared in the equations. And according to the instantaneous equations, we can calculate the RMS current for the inductor, and accordingly we can calculate the switch currents. And while we have the current equations, we can calculate the conduction loss and the switching loss of all switches available at the primary and secondary bridge. And here we can see the same waveforms as we saw from the simulations. Here the waveforms are formed according to the equations. To confirm that the equations are correct, and we can extract the same waveforms. As you can see here, the current waveform has the peak of 54, and from the simulations we have 55. That's pretty close. And to check the ZVS requirements, we need to calculate the instantaneous inductor and the switch currents, and we need to have the stored energy in the inductor to be more than the body capacitor of the switches. Here in this table we have work to reflect the different situations depending on the delta values and the different cases for the turning on the time of the turn on switches. We have different case, and we have the ZVS condition to calculate if the ZVS is happening or not. This table is for the secondary bridge, which is operating at with the conventional modulation, and here is the ZVS criteria and the ZVS checking for the primary bridge with the new modulation method that with the changes that I explained in the circuit. And then we formulated a loss optimization problem to minimize the sum of the conduction and switching losses for all 8 switches from 1 to 8, 4 at primary and 4 at secondary, while the control variables and the variables of the optimization problem are the gate control signal variables, phi delta 1 and delta 2, for the triple phase shift that's have the maximum number of control variables here. And this optimization problem is subject to the power transfer constraint. We want the power transfer to be equal to the load power, and the variable bounds, they have the minimum and maximum lower and upper bounds. For the phi could be from the negative pi over 2 to positive pi over 2, and delta 1 and delta 2 could be between 0 and pi over 2. And how we need to calculate the conduction and switching losses. Here you can see the equation for the conduction loss. It depends on the RGS on of the switch and the current switch at the RMS current switch, that we can extract the RMS current switch according to the inductor RMS current that we had from the GHA analysis of the circuit. And in this table we are showing that how we can calculate the RMS of the switches for the primary and secondary bridges depending on the modulation method. We can use the conventional for the secondary bridge and the AHFM for the primary bridge. And to calculate the switching loss, we use the typical equations for the switching loss, but for the switching on loss, it depends if the ZVS is happening or not. According to the previous slide that I explained, the ZVS criteria for the primary and secondary bridges and their switches, if the ZVS is happening, we can remove the switching on loss, and this is applying with these binary variables bi. If the bi is 0, it means that we have the ZVS and soft switching, so we can remove the switching on loss from the total switching loss, and we always have the total the switching off loss for the all switches. After running this optimization problem, we have implemented this optimization problem for a wide gain range, starting from half voltage gain to 1.2 voltage gain. And you can see different curves corresponding to the conventional modulation with single phase shift, conventional modulation with dual phase shift, CM TPS triple phase shift, and 2 modes of the AHFM method, single phase shift and dual phase shift. From 2 curves that corresponding to light load and heavy load operation, from both we can see that it's optimum to use the proposed AHFM at low voltage gain operation and then switch to the conventional modulation to maintain the maximum efficiency over the whole EV charging cycle. And here you can see the same results for the wide gain range and the power range, charging power range. And the yellow area is corresponding to AHFM method, and the green area is corresponding to the conventional modulation. And for the all power range, you can see that at low voltage gain is optimum to use the AHFM method and then switch to the conventional modulation method for the higher voltage gain. And here you can see the number of switch legs that are experiencing the soft switching. The left one is for the conventional modulation. You can see for the most area we have only one leg that is experiencing the soft switching. While for the AHFM method, it facilitates the ZVS happening, and the more switches are experiencing the soft switching. For example, for the area around the unity voltage gain, 4 legs, that means all 8 switches are experiencing the soft switching, and we have the other areas. For example, this area facilitates this soft switching for 3 legs corresponding to 6 switches, and we have 1 leg here and 2 legs in this area. And totally, comparing two figures, we can see that AHFM method can facilitate the soft switching for the counter. And if we want to check the whole EV charging cycle, here you can see on the left picture, you can see the charging curve. We have the charging current, and the red one is the charging voltage, and the black curve is the charging power of the battery during the charging cycle. The charging starts with the constant current mode and then goes to the constant voltage mode. And if we map this charging profile and we extract the trajectory of the charging in the gain versus power plane, we can obtain this curve, this black curve that starts from point A for the constant constant current mode charging, goes to point E, point B, and point C. And at point C, we are transiting to the constant voltage mode. And here, from the optimization, the loss optimization results, we can conclude that if we transit from the AHFM method, start the battery charging with AHFM method, and then transit to the conventional modulation at point E, that's corresponding to gain of 0.74 for this specific battery situation, we can maintain the maximum efficiency during the whole EV charging. And this curve shows the same results, start with the AHFM, and at the gain of 0.74, we can transit to the conventional modulation to maintain the maximum efficiency during the whole EV battery charging. And here you can see the hardware that I will explain in the video as well, with the specifications. And you can see the optimum set of control variables for different modulation methods depending on the charging power, and the corresponding RMS current and the efficiency of the circuit at different cases. And here you can see the sample experimental results for 400 volt to 200 volt conversion at 1.1 kilowatt charging. The left one is corresponding to the conventional modulation SPS, and the right one is for the AHFM. With the same situation, if you compare the current waveforms, you can see that for the conventional modulation, it has a peaky current with a maximum of 16 amperes and the RMS of 8.9 amperes, while the RMS current with the same operation condition is reduced to 6.5 amperes with the peak of 7.8 amperes, and it's a more flat profile for the current that results less conduction and switching losses and improved efficiency. And we have the same results, and the same pattern is valid for the low voltage, low charging power. You can see the same results. And here you can see the experimental results for the transition between the different modulation methods in 3 stages. Here we started for 400 to 400. That's optimum. The optimal modulation method for this conversion is the conventional modulation. Then, while the voltage, the load voltage is dropped to 200 volts, we can see the converter changes transits to the triple phase shift that provides the maximum flexibility to improve the efficiency, but the current is still increasing. So at a specific point, it transits to the AHFM method for the same half gain conversion to increase the efficiency through the minimizing the RMS current, and so it reduces the conduction and switching losses. And finally, I provided a thermal image of the 400 to 200 volt conversion at 1.1 kilowatt to see the temperature of the switches. Here for the conventional modulation, you can see we have higher temperature for the secondary bridge, and also we can see the temperature of the primary bridge. Both primary and secondary bridge switches have the very less temperature for with the AHFM method that shows that we have less switching loss and the conduction loss. So next, let's check some experimental results in the video to see the waveforms in the scope.
Now let's go to check the hardware and some experimental results. Here you can see the hardware. This is the primary board, and you can see the switches, the gate driver circuit, and this is the blocking cap to remove the offset from the square waveform. And the primary side is connected to the secondary board through the high frequency transformer. It's a planar transformer. We have the external inductors, and we also have the control board. Okay, let's check some experimental results. For the first case, I will run the circuit for the conventional modulation for a half voltage gain. We want to convert the 100 volts to 50 volts with the conventional modulation. I will start the circuit. Okay. Here we have the 4 waveforms. This is the primary voltage, primary current, secondary voltage, and the secondary current. For conventional modulation, we have the half voltage gain. We were converting 100 volts to 50 volts. And as you can see, the current waveforms are highly peaky with a maximum of 2.8 amperes and the RMS of 1.5 amperes. Now we'll run the circuit with the same parameters and the same power and voltage conversion with the new modulation to see how we can reduce the RMS and maximum current and accordingly reduce the conduction and switching losses. And now we will check the same results for the new modulation method. I've uploaded the DSP code, and I will run the circuit for 100 volt to 50 volt to check the waveforms. Okay, as you can see here, it's again for 100 volts to 50 volts conversion. And now if you compare the current waveforms with the previous case, you can see that now we have a more flat profile, while the RMS current is 288 milliamperes, and with the maximum of 380 milliamperes, which is much less than the previous case with the conventional modulation. And it means that we will have less conduction loss for the switches, and also through the theoretical analysis of the circuit, we saw that this modulation facilitates the ZVS condition, and we will have less switching loss as well. And totally, it will help to reduce the total loss and improve the efficiency of the converter during the EV charging cycle.